Hi everyone, in this lesson we're going to be looking at trigonometric identities and how to use them in equations. So trigonometric identities such as the Pythagorean identities or double angle identities are equations that relate trigonometric functions. So we have Pythagorean identities first. They're going to be derived using the Pythagorean theorem, right? If we look at the right triangle that we have shown here, we can set up all of our trig ratios, which you should already be familiar with from Algebra 2. And we can derive the Pythagorean identities using the Pythagorean theorem. So the first thing that we're going to do is we're going to derive sine squared plus cosine squared, we are 1, using the Pythagorean theorem. So what we're going to do is we're going to write the Pythagorean theorem, and then we're going to divide everything by c squared. And we're going to divide everything by c squared. All right, so that gives us a over c squared plus b over c squared equals 1. Well, if we go back to our sine of theta, that's a over c. And for b over c, we have the cosine of theta. So we can rewrite that now as sine squared theta plus cosine squared theta equals 1. So using our trig ratios and our Pythagorean theorem, we are able to show how to derive sine squared plus cosine squared equals 1. Now, there are two more Pythagorean identities that we can derive. Instead of divided by c squared this time, we're going to divide by b squared. All right, so we're going to rewrite the first term as a over b squared. B squared divided by b squared is just 1. And then we'll rewrite c over b squared. All right, a over b is the tangent, and c over b is the secant. So this one can be rewritten. Tangent squared theta plus 1 equals the secant squared theta. And lastly, we're going to divide by a squared. So we get 1 plus b over a squared equals c over a squared. b over a is the cotangent of theta, and c over a is the cosecant of theta. So we end up with 1 plus cotangent squared theta equals cosecant squared theta. So now you can understand why they're called Pythagorean identities. And these are the three that we just derived. Now we also have something called double angle identities. So trigonometric formulas, known as double angle formulas, are called this because they involve trig ratios involving double angles, such as sine 2 theta or cosine 2 theta. Now, we looked at double angles in the last lesson, but sometimes you can't solve for it easily, and you may need to rewrite it a different way. All right, so sine of 2 theta can be rewritten as 2 sine theta cosine theta, and cosine 2 theta can be rewritten in any of these forms. Right now, we're not going to look at the proofs of these. You're just going to have to trust me that these exist, and you're welcome on that. So example 2, we're given some information here, and we're asked to find the double angle. So let's go ahead and work through these. So first of all, we're told that the sine of theta is equal to 3/5. And we know that our theta is going to be between 0 and pi over 2 on the unit circle. So we know we're working in the first quadrant. So we can use the Pythagorean identity sine squared plus cosine squared equals 1. And I'll show you how we'll do that. We know that the sine of theta is 3/5. So we're going to rewrite this as 3/5 squared plus cosine squared theta equals 1. And now you can see it's going to be really easy for us to solve for the cosine of theta. So we have 3/5 squared is 9 over 25. I'm going to subtract that from both sides. So we end up with the cosine of squared theta equals 25 over 25 minus 9 over 25. That gives us 16 over 25. So our answer is plus or minus 4 over 5. Now remember, we said that we're working in quadrant 1, right? We said that we're looking between 0 and pi over 2 on the unit circle. So we know that our answer can only be positive. So we can just go ahead and erase that minus part of our answer. So the cosine of theta is 4/5. So now we found the cosine of theta. We know the sine of theta. We're going to use our double angle formula to find the sine of 2 theta. So we know the sine of theta is 3/5, the cosine of theta is 4/5, and we're just going to multiply that by 2, and we're going to end up with the sine of 2 theta is equal to 24 over 25. All right, for the same problem, we're looking for the cosine of 2 theta. Now, we already know the cosine of theta is 4/5, the sine of theta is 3/5. So we're going to find the cosine of 2 theta, and we're going to pick one of our double angle formulas. I'm going to use, you could use any of them, all right? I'm going to start off, I'm actually going to show you all three, how they all work, but you only have to pick one. So we've got, first off, that the cosine of 2 theta is equal to the cosine squared theta minus sine squared theta. So this is the first one I'm going to use, and we're just going to fill it in. So the cosine of theta is 4/5. The sine of theta is 3/5. And when we solve that out, we're going to get 7 over 25. All right, let's try another one. We could also use the cosine of 2 theta is equal to 2 cosine squared theta minus 1. Fill that guy in. Cosine of theta is 4/5. It's squared minus 1. When we solve that out, we'll get 7 over 25. Don't believe me? You can put that in your calculator or do a little mental math. And then the last one we have to look at is 1 minus 2 sine squared theta. That's going to give us 1 minus 2 3/5 squared. If we solve that out, we're also going to get 7 over 25. So again, you only had to pick one of those, but I wanted to show you that no matter which one you pick, any of them will work. As always, I like to show you in your formula booklet what's included. All right, so we have the identity for tangent. Of course, you should just know that sine over cosine. Our Pythagorean identity. The other two Pythagorean identities we derived will not be included in the IB exam. It's not in the formula booklet, and don't worry, you don't have to have those memorized. You just need to know this guy. And then the double angle identities are here. We have the sine of 2 theta, and then the 3 different ways you could rewrite cosine of 2 theta. They're all here in the formula booklet under topic 3. Okay, so we have some practice problems here. Let's get into it. We're going to solve for the sine of theta. So the first thing that I'm going to do is add 1 to both sides. All right, and then I'm going to take the square root of both sides. Now, you just want to notice that we're looking between 0 and 2 pi. Now, 0 and 2 pi means we're going to look at the entire unit circle, all 4 quadrants. And we get the sine of 2 theta over 3 is equal to plus or minus 1. So we want to look on the unit circle to see where the sign is either plus or minus 1. And if you remember your unit circle, and I'll bring that up, and here it is. And so we're looking to see where is the sign plus or minus 1. The sign is the second part of the coordinate. The sign is 1 at pi over 2, and the sign is -1 at 3 pi over 2. So let's write those down. And to solve for theta, we have to multiply both sides by 3/2. Now remember, we're looking between 0 and 2 pi. Well, 9 pi over 4 goes into 9 twice with a little left over, right, a quarter left over. So this 9 pi over 4 is out of our domain. So the only solution that is going to work for this problem then is 3 pi over 4. Okay? Let's go ahead and look at number 2. So we've got sine of 2 theta equals √3 cosine theta, and we're looking at the entire, all 4 quadrants of the unit circle. So I'm going to use the formula, the double angle formula for the sine of 2 theta, because I think that might make things just a little bit easier for me. And really the only way you're going to know that is just through practice. The sine of 2 theta is equal to 2 sine theta cosine theta. And that's equal to √3 over cosine theta. Right? I'm going to move everything over so that I have 0 on one side. So I'm going to subtract √3 cosine theta from both sides. And then I can pull a cosine theta out of this binomial that I have on the left side. So if I pull a cosine theta out, I'm going to get 2 sine theta minus √3. And be careful, you can't just divide by cosine of theta. That you would eliminate an answer that you should be getting. So be careful about that. Now what we have is 2 parts that could be equal to 0. We have either the cosine of theta equals 0 or 2 sine theta minus √3 equals 0. Solve for sine theta. So we want to know where on the unit circle is the cosine equal to 0 and where on the unit circle is the sine equal to √3 over 2. So let's go back to the unit circle. On the unit circle, the cosine is equal to 0 at pi over 2 and 3 pi over 2. And where is the sine equal to √3 over 2? So remember that we have our acronym, all students take class. We're looking for a positive sine value, and sine can only be positive in the first and the second quadrants. And where is the sine? √3 over 2. So it's √3 over 2 at pi over 3, and it's √3 over 2 at 2 pi over 3. So let's write all those down. All right, so we have 4 solutions for number 2. Solve cosine 2 theta plus sine theta equals 0. Again, we're looking at going between 0 and 2 pi. So we're including every quadrant in the unit circle. Now, that cosine 2 theta combined with the sine theta, that doesn't work for me. So I want to be able to convert my cosine 2 theta to something that just has sine in it. So let's go back and look at our double angle formulas. And for cosine 2 theta, the one that has just sine in it is this 1 minus 2 sine squared theta. So that's the one I'm going to replace in my equation. Plus sine theta equals 0. And I don't like how that looks. I want to rewrite it in standard form, and then I'm going to factor that. Now, I don't like to factor with a negative for the first term in my trinomial. You don't have to do this step, but I'm going to multiply every term by -1, and then I'm going to factor that. Now, if that's not something you want to factor, like you seeing those signs in there is making you uncomfortable, you could rewrite that as 2x squared minus x minus 1 and factor that guy. That factors to 2x plus 1 and then x minus 1. And then you could rewrite, just fill in the x's for sine now. the sine of theta equal to negative a half, and the sine of theta equal to 1. So you would go back to your unit circle and you would look to find where sine is negative a half and sine is 1. All right, on the unit circle, the sine of theta is negative a half at 7 pi over 6 and 11 pi over 6. And the sine is equal to 1, sine is equal to 1 at pi over 2. So I have 3 solutions for number 3. Okay, here's a problem that really is something very indicative of what you could see on the IB exam. The expression 32 sine x cosine x can be expressed in the form a sine bx. Find the values of a and b. So we're going to have to use our double angle formula. And if we go back and look at those, we want one that has sine x and cosine x right next to each other. All right, so this is the one that has sine x and cosine x right next to each other. So let's go back to that. So we know that we have the sine of 2x equals 2 sine x cosine x. And I want to write 32 sine x cosine x. So, well, what number times 2 gives me 32? So if I'm going to put a 16, if I'm going to multiply the right side by 16, I'm going to have to multiply the left side by 16. And we're looking, remember, to compare to this a sine bx. Well, we've done it right here. We have a sine bx. So for this problem, a is equal to 16 and b is equal to 2. Now, the only way you would know how to do some of these problems is through practice. All right, you're going to have to just get used to seeing these and get comfortable with them, and this will get easier. Now, the next part says, hence or otherwise, solve the equation 32 sine x cosine x equals 8, and we're looking at doing that between 0 and pi, which means the first and second quadrant. Now, a lot of times in IB, they want you to use what you found out in the previous part of the problem. So we know that 32 sine x cosine x is the same as writing 16 to sine x cosine x. And we know that that's equal to 8. So now I'm going to divide both sides by 16. I know that 2 sine x cosine x can be rewritten as sine 2x. That's my double angle formula. 8 over 16 is a half. And now it becomes a really simple problem that we're used to doing. We want to see on the unit circle, where is the sine equal to a half? If you look at your unit circle, the sine is equal to a half at either pi over 6 or 5 pi over 6. Multiply both sides by 1/2 to solve for x, and we get x equals pi over 12, and we get x equals 5 pi over 12. And that does fit into our domain of between 0 and pi, so we have 2 solutions for part B. Okay, last problem. Given the triangle, and we know that it has an area of 10 centimeters squared, when the sine of theta is equal to 1 over 4. So if you remember, we have looked at the area of a triangle and we've looked at a formula that uses the 2 sides and the included angle. And so that's a big hint to you that we're going to be using that formula because we have the 2 sides and the included angle. Now let's just mark up this diagram just a little bit. We have this part is theta, and this part is theta. So that whole angle right here, this whole thing is 2 theta. All right. So let's write out the formula for the area of a triangle. So across from angle B is side B, across from angle C is side C, and of course this is angle A right here. So let's fill in what we have. We know that the area of the triangle is 10 centimeters squared. Side B is x, side C is root 15. And then the sine of A, that's going to be written as the sine of 2 theta. Okay? Now we know that the sine of theta is 1/4. So we're going to have to rewrite the sine of 2 theta as 2 sine theta cosine theta, and we'll end up needing to figure out what the cosine is. So let's rewrite it first of all. And that's wonderful, except for we don't know what the cosine of theta is, so we're going to have to use our friend sine squared plus cosine squared equals 1. Remember, we can always use this Pythagorean identity when we want to either solve for sine or cosine, and we have one or the other. So we get the cosine of theta is equal to positive root 15 over 16, or maybe a little nicer to write is root 15 over 4, because the square root of 16 is 4. And we know it's positive because we're using a triangle, and we can't have any lengths that are negative. All right, so we're almost done. We have all of our information, right? We have our sine of theta, which we're going to put here. We have our cosine of theta, root 15 over 4, which is going to go here. And now we're able to solve for x. So let's fill it all in. All right, so on the right side of the equation, if I multiply everything out, I'm going to end up with 15x over 16. And now I just solve for x. So I'm going to multiply both sides by 16 over 15. So I'm going to get x is equal to 32 over 3. And that's our final answer. Now, it might seem like a lot. Sometimes you have no idea where you're going to go with the problem, but my advice is always you just have to try something. And you have to have that formula booklet handy so that you can use that as a guide. What formulas could fit in here? Your first clue in this problem is they're talking about the area of a triangle, and you pretty much know you're going to end up using this one, not the simple one from 4th grade that was 1/2 base times height. And then you say, oh, in that formula, I end up with the double angle formula. You go back to your formula booklet, rewrite it. You get to that point, you say, oh, I only have the sine. I have to find the cosine. Go ahead and use your friend, the Pythagorean identity, to find the cosine. And before you know it, this really hard problem, you've gone through it step by step. You keep inching your way towards the solution. All right, everybody, that's all I have for this lesson. You're going to need a lot of practice, so hang in there. Thanks for watching. Have a great day.